So is P1 equal to, is it less than, or is it greater than P2? All right, well, most of you said C, right? You said that it's greater than. What would happen if P1 was actually bigger than P2? I had a big pressure here and a small pressure here. It would fall out, right? It would just fall out. Even if they were equal, it would also fall out because just the weight of the fluid would cause it to fall out. So here, my P1 is less than P2, and since pressure is force per unit area, that's actually what's keeping the force that's keeping that water up in the straw. All right? So let's go back to this wicked-looking guy on the left. What is the pressure? Describe to me in your words, what is the pressure that causes the straw to work? The what? Close. She said the pressure inside the container. Close, that's what she said, right? The pressure of the water in the cup? Close, but that's not exactly right. Huh? What do y'all think? Is it in his mouth? Is it? Okay, let me just tell you. It's not the straw. Right, there's a pressure that's pushing down on the outside of this surface. This is our atmospheric pressure, right? And then, you know, he does put a pressure here. I'll call this the pressure due to his mouth. But it's not actually that pressure, PM, that causes the liquid to go up into the straw. He puts a low pressure on the straw, but really the pressure that pushes the liquid up into the straw is the atmospheric pressure. Because as he makes a low pressure inside of his mouth and inside the straw, this pressure pushes down and pushes it up into the straw. In much the same way as this happens right here, that the atmospheric pressure actually pushes the liquid up and holds it into the straw. It just so happens that this is a low pressure, but it's actually the pressure that's pushing up that causes it to stay in the straw. And this should be causing you to think, that's interesting. Shouldn't there be like a theoretical limit to the length of a straw? Is that what y'all were thinking? There is, in fact, a theoretical limit. Because at some point, remember P is equal to rho GH. And P is equal to 1 atmosphere. The pressure at 1 atmosphere is 1 times 10 to the 5th newtons per square meter. All right, so if I do 1 times 10 to the 5th, the density of water, you don't need to know these numbers. I'm just trying to show you that we have this theoretical limit. The density of water is 1,000 kilograms per cubic meter. G is equal to 10. H, and then this is 1 times 10 to the 5th. That's 1 with 5 zeros on it, newtons per square meter. So if I solve this for H, then H is 100,000 divided by 10,000. H is 10 meters. So that means that if you have a straw that's longer than 10 meters, you cannot use it because the atmospheric pressure is not strong enough, is not big enough to push that liquid up into the straw. And you think, well, that doesn't really make any sense, does it? Do you think that you could use a 10-meter straw to draw water up into it? Well, you can't use a 10-meter straw. It's impossible. I have a little video I'm going to show you. It's from Veritasium. We won't watch the whole thing. We'll just watch a few minutes of it. But if you want to go back and later watch the whole thing, you're welcome to. Let me pull it up. It's fairly interesting. I think it's interesting. Go on and try to use a 10-meter straw, where they have that plastic tubing that's 10 meters long, and they go to this big cliff, and they try to suck water up through it. And they're not able to do it. It's actually very, very difficult to do so. In that clip, actually, they went from a very thin straw to a bigger straw. I think they increased the diameter by a factor of 2 or so, and he wasn't able to draw the liquid up into that 6-meter length. But technically, that really shouldn't matter, because if you look at this expression for pressure, that rho GH, there is no talk about the diameter. It's only the diameter of the column of liquid. It's only the height of the column of liquid. So the pressure that I have, like let's say that I have a column that's this big and filled with liquid. This pressure, P1, would be exactly the same as if I had a column that looked like this that was also filled with liquid P2. Those would be exactly the same. It's not dependent upon the diameter. Now, with their little experiment where they go to the bigger diameter straw, why do you think that would matter? Why is it more difficult for him to draw liquid up into a bigger diameter straw than a smaller diameter straw? What's that? Mariah? No, it's not really the flow rate. That's a good, yeah, like the Poisson equation. Yeah, that's a good guess, but no. Elise. Alyssa. Sorry. I was trying to, Alyssa. You're, Alyssa. What'd you say? There's what? No, no. It's really sort of a side thing. If you have that bigger tube, you have the atmospheric pressure pushing in on all the sides, it's just easier to collapse. Right, have you ever tried to suck liquid through a tube and it just sort of collapses down on itself? Like siphon gas or whatever? You don't siphon gas, do you? Gosh. I almost be from the big city. We siphon gas all the time because my uncle had several vehicles and one of them was always running out of gas, right? And so he had a little section of garden hose he'd keep behind his seat in one of his trucks. If you ran out of gas, you just get gas from one of them, right? And so you have this gas tank. You put this section of hose down into it. You suck on it like it's a straw, and you draw the gas up into the here. You have that pressure inside the gas tank pushing it up into the hose, and eventually it's going to come out and either go into your mouth or, if you're really good at it, go into the gas can. Y'all should try it. It works. All right? Okay, so that's pressure due to weight. Now let's look at the third thing, which is the pressure due to an external force. The pressure due to an external force, this is a principle called Pascal's Principle. And Pascal's Principle says that if you have a pressure at any one point in an incompressible fluid, then that pressure is felt all the way throughout. So first of all, it only applies to incompressible fluids. That just means that you can't compress them, or you can't make them smaller. If they have a certain volume, that volume is fixed. Remember, fluids include gases and liquids. So when I say incompressible fluids, what am I really saying? Of gases and liquids, which are incompressible? Liquids, right. So liquids are incompressible. Practically all liquids are incompressible. Water is incompressible. Hydraulic fluids are incompressible. Oil, practically all liquids are incompressible. So when I say incompressible, I really mean liquids, not gases. So this does not apply to gases. So it applies to incompressible fluids or liquids. And he said that when pressure is applied to to a fluid in a closed container, or we'll just say liquid, when pressure is applied to a liquid, in a closed container, the change in pressure, that's what this symbol means, the delta, the capital delta P means a change in something. The change in pressure is felt throughout the entire liquid. Let me show you what I mean. So if I have say a piston, it looks like this. It's closed. I can apply a force to it. This is just a piston. It's filled with a liquid. If I apply a pressure, if I apply a force per unit area, up here on this piston, then that change in pressure, that extra pressure that I give it, is felt all the way throughout. So that pressure is felt here, that pressure is felt here, that pressure is felt here. It's felt all throughout the container and everywhere in the liquid. This is a nice thing if I want to use, say, if I want to lift something that's really heavy. Right? We all use hydraulic lifts in one way or another. A hydraulic lift looks like this. A hydraulic lift is only 2 pistons. By the way, I don't think that your book does hydraulic lifts. I'm pretty sure that they don't. But I do want you to know how to do this for the test. You will see a hydraulic lift problem where you apply one pressure on one end and you need to figure out the force. Don't worry, it's not that hard. I'll show you. So this is a hydraulic lift. I have one section down here. I apply a force. I'll call this F1. This is the area A1. And so the pressure down here, P1, is equal to F1 over A1, right? Force per unit area, that is my pressure. Down on the other end, I have the piston closed off. I have a force, I'll call this F2. I have an area, A2. And so the pressure here is F2 over A2. What Pascal's principle says is that P1 is equal to P2. That any pressure that I exert on this liquid over here, I'm going to feel that same pressure all throughout. It's going to be transferred directly to this piston over here. So that this pressure, P1, has to equal this pressure. And so we can use that in order to our advantage, like a simple machine, basically. Let me show you. We'll put in some numbers here. Let's imagine that my area, A1, is equal to 1 square meter. It's a pretty big piston, 1 square meter. And F1, I don't know, let's say that I put in 100 newtons of force. That means that my pressure, P1, is going to be 100 newtons per square meter. 100 divided by 1. Now, let's say that A2, on the other hand, is 10 square meters. It has a bigger area. Do you think that F2 is going to be bigger, smaller, or the same as F1? Am I going to get a bigger force out of that bigger piston or a smaller force? It's not going to be the same. It'll be bigger or smaller? What do you think? F2. It is going to be bigger. It's going to be by what amount, Gina? By a factor of 10. My area is a factor of 10 bigger, so my force is a factor of 10 bigger. We could work through it, right? So I want to know what F2 is. And so I say F1 over A1, that's 100 over 1, is equal to F2 over A2, which is 10 square meters. And then I can solve this, and I find that F2 is equal to 1,000 newtons. All right? So I get, because my area is 10 times as big, I get 10 times the force. You use this on hydraulic lifts, like to lift cars. If you imagine, you have a car on this end. I have a car here. And then over here, I only need to put in a small force in order to lift that car. Use it with your jacks too, like if y'all have one of those floor jacks to lift your car up. You notice where you're pushing it down, if you look at the bottom of the handle, there's a little piston there where it's going into the hydraulic system, and then it attaches to a bigger piston that causes the jack to lift your car. You have it with lifts and stuff like you lift people with. You see hydraulic lifts a lot if you start looking around. You'll see them a lot sort of in your life. All right, so be able to work a problem like this. The numbers will be simple, but basically what you're looking at, your force is the same amount bigger as the area. So if your area is 3 times bigger or 4 times bigger or 5 times bigger, then your force is going to be the same amount bigger. So if you just remember that should do you just fine. All right? Dad worked at a tire store my whole life. Now, I have three brothers, and so we all worked there as well. And we would, play with the hydraulic lifts a lot. Okay, let's see. That is pressure due to an external force. Let's look at three different pressures. First of all, though, imagine a tire. Like, let's say that you have a tire. How much air pressure do you put in a tire? About 35, right? 35, and that's measured in what? PSI, which stands for... No, it's not pressure. Remember, pressure is force per unit area, so PSI must in some way refer to the force per unit area. Pounds per square inch. Thanks, Christine. Yeah, so SI, pounds square inch, pounds per square inch. All right, so PSI measures a pressure. It's a force per unit area, or pounds per square inch, which is the British system. We use newtons per square meter, but in the British system, they use the pounds per square inch. So what if you lose all the air in your tire? What is the pressure inside the tire now? Your tire is completely flat. What is the pressure inside your tire? It's not zero. It's what? What is the pressure right here? The atmospheric pressure. That's right. So the pressure right here is 1 atmosphere. In a sense, it is zero, and we'll talk about that. There are different types of pressures that you can imagine. You have an absolute pressure and a gauge pressure. I think there's a third. Yeah, and then the gauge pressure, the atmospheric pressure, and then the absolute pressure. You need to know that be able to distinguish between those three types of pressure measurements. The first is gauge pressure. And when Marissa said that the pressure inside the tire was zero when it was flat, she was referring to the gauge pressure, right? If you look at the gauge pressure on the tire, then yeah, you would say that it is zero. This is just simply what the gauge reads. I'll show you a video in just a second how they make these gauges. It's pretty cool, actually. So the gauge pressure is what the gauge reads. The other pressure that we have is atmospheric pressure. And this is just the pressure due to the atmosphere. And then the third one is our absolute pressure. And the absolute pressure is the sum of these two. And that is equal to the absolute pressure is equal to the gauge pressure plus the atmospheric pressure. And so when I say to Marissa, I say, no, it's not zero. I'm talking about the absolute pressure, because the absolute pressure on that tire, it doesn't have, your gauge doesn't read anything, but it does have a pressure. It's the same as the pressure that we feel around here. Okay? So know what those three pressures are. Now, let's watch this video just about gauges, how gauges are made. It's fairly interesting, but you're not responsible for. All right, so that's another way to measure pressure. It's a little different from the manometer. The manometer, remember, you're comparing two pressures. Here you're comparing a pressure that's unknown to the pressure that's in that little coil of pipe. So you put in a force per unit area into it, and the way that that pipe moves, I forget what they called it, but that allows you to measure that unknown pressure. All right? All right, so let's look at the third source of pressure, which is the interaction between molecules. You've probably seen this before in chemistry or high school science. It's the ideal gas law. So you can have pressure due to a column of liquid that's sitting on top of your head, or a column of a fluid that's sitting on top of your head that's pushing down on you. The gravitational force causes a pressure. You can also have a pressure that's due to an outside force, like in the hydraulic machine. And then the third thing is you can have interaction between particles. So like in this room right now, there are all sorts of gas particles, and they're all zooming around at pretty high speeds. And the way those particles interact will actually cause a pressure inside the room. So let's consider a container of gas. This is a closed container of gas. Otherwise, you can't really have a container of gas, right? If it's not closed, the gas will just leave the container. But it is a closed container of gas. If you add gas to the container, what will happen to the pressure? Will the pressure remain constant? Will the pressure go up? Or will the pressure go down? What will happen to the pressure? Will the pressure go up or remain constant, go up, or go down? I have this container of gas. I put gas into the container. What happens to the pressure of the gas in the container? Your intuitive answer is probably the correct answer, so just sort of go with what you think. All right, I'll stop at 32. 32. Okay, awesome. B is right. If I stuff more gas into that container, the pressure is going to go up. And we'll see how that falls out mathematically. What if you increase the temperature of the gas? Which of these will be true? Will the pressure remain the same? Will the pressure go up? Or will the pressure go down? So if I add the gas container, the pressure goes up. What happens if I increase the temperature of the gas? Which of these? The pressure remain constant, go up, or go down? All right, I'll stop at 33. Just guess if you're not sure. Okay, maybe that's not so intuitive, but the right answer there is B. If I increase the temperature, think of a balloon, right? What happens if you heat up a balloon? It gets bigger and bigger and bigger because as you increase the temperature of the gas, the pressure increases and it causes it to increase. So this can all be summarized in the ideal gas law, which says that the pressure times the volume is equal to N times R times T. Let me show you what these mean. P is the pressure, V is the volume. If we assume that the volume remains constant, right, in a container, N is the amount of gas, R is just a constant, don't worry about it, and then T is the temperature. I more want you to be aware of the relationships between these. So like if I hold my volume constant, if I increase N, that will cause P to increase. If I increase T, that will also cause P to increase. Or what happens if I decrease the volume of the container? What will happen to the pressure? It'll go up, right? So if you have a container that's filled with gas and then you make that container smaller and smaller, the pressure of the gas inside the container will increase. All right, this is called the ideal gas law. I'm pretty sure that everybody's seen it at some point in your life, but it's called the ideal gas law. Know how those different relationships act. There is a special case of the ideal gas law. It's called Boyle's law. They talked about this in your book. Boyle's law, actually the ideal gas law was a collection of laws that were sort of brought together. And Boyle's law assumes a constant temperature, or it assumes constant N and T. So a constant amount of gas, that's N, and a constant temperature. So basically Boyle's law says that pressure times volume is equal to a constant value. We'll see this a little bit later in the second part of the chapter, but you use this every day, that pressure times volume is equal to a constant. Because if I change the volume of something, Like if I increase the volume of something, what happens to the pressure? If V goes up, what has to happen to P? It has to go down. And if V goes down, what happens to P? Goes up. So imagine that you're breathing. How do I breathe? When I actually bring air into my lungs, what am I doing? My lungs aren't muscles, right? They don't suck in air in any way. What are you doing? You're expanding the volume of your chest cavity, right? So I expand the volume of my chest cavity, I make V go up, and then that causes P to go down. So everybody, expand your chest cavity. Right, you're making it bigger so that you get a lower pressure inside of your chest, inside of your lungs. Your lungs sort of fill that space, and that causes air from the outside to rush in because you have high pressure out here, low pressure inside. And then when you expel air, right, you make your chest cavity smaller, and that causes, if P goes down, or excuse me, if V goes down, P goes up. That causes high pressure inside your chest cavity, expelling that air. All right, just a couple more things, and we'll wrap it up. We can also have pressures in solids. They're not in the same way as when we think about it in liquids and gases, but it's more that solids can feel pressure. So in your book, they talk about a high heel. Y'all wear high heels? Nobody does here, I don't think. But high heels, which have a very small area, I mean, not today. I'm sure that y'all might wear high heels. I don't know. Never mind. High heels, which have a very small area, even if you apply a very modest force to them, they'll have a very high pressure. So imagine that you have, a lady, I don't know, 120 pounds, 130 pounds, and she has high heels that have an area of, say, 0.1 square inches. Now, if you calculate the pressure that's on that, say she's standing just on one heel, the pressure is going to be our force divided by our area, which is 120 pounds, divided by 0.1 inches squared. That's going to be a pressure of 1,200 psi, or pounds per square inch, on that heel. Now, in contrast, if she's wearing sneakers, sneakers have, I don't know, 24 or 30 square inches. So in contrast, the pressure in sneakers is going to be force per unit area. That's going to be still 120 pounds divided by 30 square inches, because that's roughly the size of the bottom of your sneaker, right? It's maybe 12 or 13 inches in this direction and 3 or 4 inches in this direction, so about 30 square inches, a little bigger or smaller depending on how big your foot is. That is just 4 psi. So you see you can have a pretty drastic difference depending upon the area, that if you have a very small area, then you get a very large pressure. All right. I have a few questions. Let's just go through a few of these clicker questions. I'm going to put them online for you so you can see them. I don't think we'll have time to go through all of them, but let's just try doing a few of these. Consider what happens when you push a pin and the blunt end of a pin, like a writing pen, against your skin with the same force. What will determine whether your skin will be punctured? Is it the pressure on your skin, the net applied force on your skin, the pressure and the net applied force are equivalent, or is it neither pressure nor net applied force are relevant? I have a pen which is really sharp on the end, or a writing pen which is blunt on the end. What will determine whether your skin will be punctured? You push with the same force on both the push pin and the writing pin. Ask your neighbor if you like. Y'all are sort of all spread out. The answers are just, they're all over the place. me tell you that it's not C, okay? That it's not C. It's not both of them. Okay. All right. I'm going to stop at 122. 122. All right, so the answer is A. It's the pressure. It's like the sneaker versus the high heel, right? Who would you rather step on your toes? A lady in sneakers or a lady in high heels? The sneakers, for sure, because that's not really going to hurt much at all. What, 3 psi? Is that what it was? Versus the 1200 psi? So it's very much the pressure on your skin that you're concerned with. You're walking out on a frozen lake and you begin to hear the ice cracking beneath you. What is your best strategy for getting off the ice safely? I did this just the other day. I was out in the bayou. Frozen over. Ice started to crack. All right, I'll stop at 45. 45. Okay, E is right. Because when you lie down flat, that increases your area and it gives you a lower pressure. Sneakers versus high heels, right? Which are you gonna? You want to increase your area to decrease your pressure. We're running out of time, so I'm gonna go through some of these. We talked about that one. We did this question as well. Okay, let's do this one. We talked about this, but I'm not sure if you caught it. Let's just make sure. In a mercury barometer, a barometer is a lot like a manometer. We'll talk about it later. It's not important for this, but the height of the column of mercury is 760 millimeters. You have over 760 millimeters of mercury. That's where that comes from. If another mercury barometer has a tube of larger diameter, how high will the column of mercury be in this case? So if a bigger diameter tube, will the column of mercury be greater, less, or equal to 760 millimeters? Okay, doing a pretty good job. I'll stop at 52. Okay, C is right. And as I heard somebody saying, the pressure is not dependent upon the area. It's only dependent upon the height. Okay, the area of the tube doesn't matter. That's like the whole thing with the straw on Veritasium with Derek and his friend Nigel. We'll see. We're gonna. Okay, so can I see somebody's book? May I borrow your book? Carry on, right? No, Deja. So in your book, we're not getting up to fluid flow. We are not doing fluids flow. So we'll have chapter 1, chapter 2, chapter 0. Don't forget about that one, okay? Because you will have some questions on that. So in your book, that takes you up to page 41. It says fluids in motion up to that point, up to fluids in motion. Okay? That's on Thursday, whole class, yada yada. Any questions? Okay. Y'all have a great day, okay?